and welcome to 9.1. We're dealing with quadratic functions and projectile motion. So let's look at this first example. A baseball batter pops a ball straight up. The ball reaches a height of 68 feet before falling back down. Roughly 4 seconds after it is hit, a ball bounces off home plate. Sketch a graph that models the ball's height in feet during its flight time in seconds. When is the ball 68 feet high? How many times will it be 20 feet high? Okay, so the first thing we're going to do is we are going to mark this graph. Alright, so I think since we're only going 4 seconds, we have to go all the way across. We can probably have a pretty good tick marks along here. I think every 4, 1, 2, 3, 4. There would be 1 second, and we'll do the rest of it. And then since we're going 20 feet high, or 68 feet high is the highest, I need to go up to 70. So I think if I go every other would be 10, that will be good. Alright, so I've put these on here. So now let's take a look. Well, we know that the ball will get back to the ground at 4 seconds. So what we're going to do is let's go ahead and put 4 seconds on 0. Alright, let's see if this is actually going to work this time. Right about there. I know that the ball is going to be hit probably about there, somewhere between 0 and 5 feet, right? Because that's about where a batter would hit the ball. And then the ball is going to come up and come back down, right? So when it goes up and comes back down, right in the middle is where it's going to reach its highest spot. It's very symmetrical that way. And all parabolas, which is the graph of a quadratic, which is what we're going to be focusing on this chapter, are always going to be very symmetrical. So we're going to say right around 2 is when it's going to reach its highest point of 68 feet. So at 2, it's going to be right about 70, so we're going to go right about there. Alright, and then what we're going to try and do is we're going to try and just make this look nice and smooth. Alright, so it's not going to be too linear. We don't want it to be too pointy. We want it to be nice and smooth. Alright, so we're going to look something like this. There, and then it gets to 0, and it's going to start to come back down. Alright, and that's a pretty good graph of what we're looking at. Alright, so if we can really draw it smooth, it wouldn't have some of these marks in there, but that's pretty good. Okay, so when is the ball 68 feet high? The ball is 68 feet high at, well, that's really thick. It's going to be 68 feet high at about 2 seconds. Alright, so at 2 seconds, the ball is 68 feet high. So now the next question is, how many times will it be 20 feet high? So if I look at 20, and I make just a line and say, how many times does this graph hit this 20 feet? Well, it looks like it hits it here and then here, right? So how many times did it hit 20 feet? Well, it's 20 feet high. It should be 2 times, right? 2 times because it's got to go up to 20 feet, it travels higher, and then it comes back down, and it's got to hit it again before it hits the ground. Okay, and we can say that's at about 0.25 seconds and probably at about 3.75 seconds, if we wanted to ask. It doesn't ask, but we could say it is at about those 2 places. Alright, so this is the general parabola. This is what the graph looks like, and we'd say this is how the ball would travel. Now notice this isn't what it would actually look like. This is saying at time 0, time 1 second, 2 seconds, 3 seconds, 4 seconds. So this isn't like saying here's the batter and here's the catcher. This isn't how far it traveled. It's just how much time passed and how high did the ball go. Alright, so then let's look at our second example. And the investigation, you approximated solutions to a quadratic using tables and graphs. Later in this chapter, you will learn to solve quadratic equations in the general form y equals ax squared plus bx plus c using symbolic manipulation, meaning algebra. Until then, quadratic equations must be in a certain form for you to solve them symbolically. You will combine the undo and balance methods on this form in the next example. Alright, so what we are going to do is now let's solve this thing symbolically. Check your answers with graph and a table. Alright, so what we're going to do is we want to figure out when is this thing equal to 47. So it's kind of like we have our function, and we're saying when is it going to be at 47. So when is it going to be at 47? Kind of like saying when is the baseball going to be at 20 feet. Alright, so we want to know when is this thing going to be at 47, and we have up to 2 options. So what we're going to do is I'm just going to rewrite it, 5x plus 2 squared minus 10 equals 47. Okay, so the first thing we're going to do is we're going to undo any addition or subtraction, right? We're looking for addition or subtraction. Then we want to undo any multiplication or division. And then we want to undo any exponents. And then we want to undo any parentheses. So do you see addition or subtraction? Well, here's some. So we're going to add 10 to both sides. Alright, so then I get 5 parentheses x plus 2 squared, and that's going to equal 57. Okay, then we're going to divide by 5, right? Because we have division next, and this is 5 times something, so divide by 5. Divide by 5. And I get x plus 2 squared equals, well, 5 goes into 50 10 times, and 5 goes into 7 several other times. So we're actually going to figure out what that number is, and we're going to write it as a decimal. And 57 divided by 5 is 11.4. Okay, so now I kind of ran out of room. I'm going to rewrite the rest of it up here. Okay, so now what do I want to do? I want to get rid of a square. Alright, so that means I should take the square root of both sides. Alright, I want to take the square root of both sides, and that will get rid of the square. But when I take the square root, remember we had a bell ringer the other day that said, find the numbers x, find x such that x squared, I'll rewrite it, x squared equals 49. And we said we should have two answers, right? X equals 7, but x could also equal negative 7, right? Because if I take negative 7 squared, I get positive 49. So that means when I get rid of the square, I have to have two answers. So I'll be left with x plus 2 without the square, and now I don't need the parentheses anymore. And now I need the both positive and negative answer of the square root of 11.4. Okay, so now I have two answers, positive and negative square root of 11.4. And then I'm going to, the last thing I do is I just have addition, so I have to subtract 2, and I'll get x equals, and I would prefer to write the negative 2 first and say negative 2 plus or minus the square root of 11.4. Okay, now if you haven't really seen that plus or minus before, all we're really saying is that we can say x equals negative 2 plus the square root of 11.4, and x equals negative 2 minus the square root of 11.4. Kind of like we're saying we have a positive 7 and a negative 7, we have a positive 11.4 and a negative 11.4. Okay, so you can leave your answer like that. If we're just doing symbolically, that's all we really need. If we want to have it be an exact answer, like we're saying, when does this ball hit the ground, if we're talking about a baseball, and these are some restraints on the baseball, and we say, well, how many seconds would that be? Well, we might want to figure out what number this is exactly. So if you were to do that, you get about 1.38 for this one. And the other one is negative 5.38. All you have to do is type in some stuff. Type in the square root of 11.4, and then take negative 2 minus that number, and you get these two. So these two would be the approximations. These two would be the exact answers. All right? So there you go.